Okay. Today is January 5th. I'm sorry, February 5th, I mean. Welcome to your new seats. We have some book work for the first time in a long time. So it turns out that sine and cosine graphs are the most important and essentially the graphs that I care the most about. Today we're going to talk about tangent and cotangent. And then Thursday we'll do secant and cosecant. Secant and cosecant are pretty easy. As long as you know how to graph sine and cosine, those just have one extra step and it's really simple. Okay. So kind of nice. Tangent and cotangent look very, very different. So we sort of have to start over with tangent and cotangent. And we'll talk about domain and range, which you really need to know, pay attention to. So here we go. Graphing tangent. So again, we have our unit circle, which is where all of this comes from. And we're just going to basically go around the unit circle to find some nice points for our basic tangent function. We'll talk about the period and the asymptotes as well. So I'm going to go ahead and do a little XY chart over here. X is between negative 2 pi and positive 2 pi. So we're actually doing 2 rotations of our circle. We're going from negative 2 pi and wrapping around to 0 and then keeping going again until 2 pi, which is weird. But we're going to have tangent of x equals our y value for our graph here. I'm just going to start at 0 radians. So right here at 0 radians, what's the ordered pair? 1, 0. Good. How do you find tangent? Tangent of 0. How do we find the tangent if we have those ordered pairs? Tangent of 0. Sine over cosine. Yeah, the sine over the cosine. So that would be 0 over 1, which is 0. So we have the ordered pair 0 radians, 0 for the tangent value, tangent ratio. I'm going to go here to pi over 4 because that is a very good one. What's the ordered pair at pi over 4? Radical 2 over 2. Yeah, all the over 4s have the radical 2 over 2 ordered pairs. And so again, if we wanted to find the tangent at pi over 4, sine over cosine, what happens when you divide those two things that are the same? You get 1. So at pi over 4, which I'm going to just call this pi over 4, we get a value of 1. And then I'm going to come up here. This would be pi over 2. What's the ordered pair at pi over 2? 0, 1. The tangent at pi over 2, again, sine over cosine would be 1 over 0. What's that? Undefined, yeah. When the 0 is under, it's undefined. So at pi over 2, we actually have an asymptote. That's very interesting. You know what? I kind of want to go the other direction and see what happens. So I'm actually going to go down here, which I can call negative pi over 4. Can I do that? Yeah? Okay, what's the ordered pair at negative pi over 4? Radical 2 over 2 and negative radical 2 over 2. Okay, that's interesting. So if I have the tangent of negative pi over 4, that'd be the y-coordinate over the x-coordinate. What do you get when you divide sine over cosine? Negative 1. So at negative pi over 4, we have the value negative 1. Huh. I wonder what happens at negative pi over 2. What's the ordered pair at negative pi over 2? 0, negative 1. And the tangent of negative pi over 2, tangent would be sine over cosine, or y over x. So negative 1 over 0, which is undefined again. Oh, interesting. Negative pi over 2. Huh. Curious. It's not a line. It is kind of like a cubic function in shape. This is one period of the tangent function. If I were to go to 3 pi over 4 pi, 5 pi over 4, 3 pi over 2. At 3 pi over 4 right here, our tangent value is negative 1. At pi, negative 1, 0. 0 divided by negative 1, we're back to 0. So you can see it just starts to repeat itself in this sort of curve. And then we'd have another asymptote at 3 pi over 2. So this is the basic tangent function. You can graph it to see. Oh, I'm in parametric mode still. I'm going to go back to function mode. Tangent of x. And I'm just going to do a trig window. So zoom trig is zoom 7. Zoom 7. And so you can see this is the tangent function. It's kind of got that same cubic sort of shape, but that sort of stretchy S shape. Okay. And so there's a few things you need to know, which this is your basic tangent function. It's an odd function. Odd means it's symmetric with respect to the origin. You can see that it passes through the origin, and we have this ordered pair pi over 4, 1. That gets reflected through the origin, and both signs change. Opposite x's, opposite y's. That was the definition of an odd function. Passes through the origin, and it has symmetry. If you fold it in half and then fold it in half again, it'd lay on top of itself. It's very weird. Anyway, and so they basically look like this. And so what we want to be able to answer then is, first of all, what is the period of the tangent function? The period is the length of time or length of radians that it takes to repeat itself. And so you can see at negative pi over 2 and at pi over 2, we have that asymptote where then it starts to repeat itself. So these asymptotes are really good indicators. And if we wanted to find the length of that, then we would subtract this ending minus the starting. So pi over 2 minus the negative pi over 2 gives us 2 pi over 2, which is pi. The standard period for a tangent function is pi. How is that different than sine and cosine? What was the standard period for sine and cosine? 2 pi. You got to know this, okay? So we have asymptotes. The vertical asymptotes for this tangent function: negative 1 pi over 2, 1 pi over 2, 3 pi over 2. What are the other asymptotes? Thinking about patterns. Negative 1 pi over 2, 1 pi over 2, 3 pi over 2. What's another? 5 pi over 2. What else? 7 pi over 2. What else? 9 pi over 2. How do we know? What is the pattern that we're seeing? Odd. Multiples of pi over 2. There's lots of ways that we can, and also the negatives. So -1, -3, -5, pi's over 2. So we can say that x, vertical asymptotes are x equals, you can say lots of things. Odd multiples of pi over 2. We could say stuff like x equals k pi over 2, or k is an odd integer. All right, so there are lots of ways we can say that. K is an odd integer. What are integers? Numbers. Good. They're a little more specific than numbers. 5, -5. They are positive and negative whole numbers, integers. Positive and negative whole numbers. Okay. There's lots of different ways that we say that sort of stuff. I'm more interested in that. You can find them. And they come from the unit circle. And so we have the domain. What values of x work? All reals except, which things do we have to get rid of? The odd multiples of pi over 2. All the asymptotes we have to exclude. So we would say everything except odd multiples of pi over 2. So that's what I would say. And what's the range? How low does this curve go? How high does it go? Infinity, yeah. So negative infinity to positive infinity. All right, that is your basic tangent function. How do I remember this? Well, first of all, you could graph the base tangent function anytime you wanted to, just plugging it into your calculator. So if you could remember, the way that I remember tangent is that it goes through the origin, centered on the origin. And I always think tangent, toes to nose, at toes to nose, low to high. Does that make sense to you? I'm so weird. But that's what tangent, toes to nose, T, N, tan, toes to nose. I don't know. But you'll notice I'm moving from left to right. This tangent is an increasing function going uphill from left to right. Toes to nose. Okay. Thanks. Let's move on. So graphing cotangent, I shouldn't have done this big domain range here. So cotangent, I don't have a cotangent button on my calculator. So if I wanted to graph cotangent on my calculator, what would I have to type in, do you think? We've got a couple of options. Well, oh, very good. So you could graph 1 over the tangent of x in your calculator. Is there another option? How else do you get cotangent? Cosine over sine is another option. Cosine of x over sine of x. So there's a couple of different ways. And in fact, we could have done tangent of x is sine of x over cosine of x if we wanted to. That's that quotient identity. And should we see 2 different graphs, or should they be the same? They should be the same. So it's graphing the first one. Now it's switched to the second. It's working really hard on the second one, but it's done now finally. So, so you can see that that's another way we could have graphed it, but we have a tangent button, so that's pretty nice. So let's go back to our unit circle. And I don't think I'm going to do the XY chart, but let's just start at 0 radians. So at 0 radians, which is our x-axis here, we have the ordered pair 1, 0. How do we find the cotangent at 0? Cosine over sine. So that's going to be 1 over 0, which is what? Undefined. Yeah, so at 0 on the x, it's actually got an asymptote right there for the cotangent function. At pi over 4, we have our ordered pair radical 2 over 2 and radical 2 over 2. What's cotangent? Cosine over sine would give us 1. Pi over 4, we have an output of 1. At pi over 2, we have the ordered pair 0, 1. Cosine over sine would give us 0. So at pi over 2, it's 0. And let's see, at 3 pi's over 4, we're at negative radical 2 over 2, radical 2 over 2. What's cosine over sine going to give you there? Negative 1. So at 3 pi's over 4, we get negative 1. What happens at pi? That'd be cosine over sine. So negative 1 over 0 is undefined. So at pi radians, we get undefined. So there's another vertical asymptote. So this is the cotangent graph. This cotangent graph is a decreasing function going downhill from left to right. Where's the next asymptote going to occur? At 2 pi, we'll have another asymptote. 1 pi, 2 pi, 3 pi. You can see, and this is how it is. At negative pi, there'll be another asymptote. It just repeats itself. Right in the middle, it'll pass through 0. And that's good enough. Asymptotes and a point in the middle is really all we need. You can see that it's a decreasing function. And we want to know, what are all the vertical asymptotes? How can we describe all those vertical asymptotes? X equals 1 pi, 2 pi. What are some other asymptotes? 3 pi, 4 pi, 5 pi. How would you describe those? That's domain, yes. So I would just say multiples of pi. You could put k pi where k is an integer. An integer, remember, is positive and negative whole numbers. So k represents -1 or -2 or 0 or 2 or 3 and so on and so forth. There's a 1 in there as well. So k represents any integer. And it's good to start thinking like that because we are going to need that eventually to understand what k can be. So then if we know that those are the asymptotes, how do we describe domain? What x values are allowed? Yeah, I'm not to those. All reals except x equals k pi, where k is an integer. We actually have special symbols for integer as well. Like this bold-faced R stands for the real numbers. There's actually a bold-faced letter that represents integers. I'd have to look it up, but I think it's like a Z. It's very weird. Why don't you just use I? I don't know. It's weird. Okay. And again, the range is from -infinity to +infinity. Cotangent. So cotangent to me, when I put on my coat, it goes like my shoulders down, right? Like when you wrap a coat around you, right? Use shoulders to toes. Okay, does that make sense? That's your coat. You're putting on your coat, top to bottom. Okay, don't ask. Okay, but that's how I remember. It's a decreasing function, and it's shifted. You can see this is not odd anymore. It's not even either. It's a neither function, but it's been shifted over. Starts at 0, ends at pi, and that's really important. And in fact, those two asymptotes at 0 and pi are very useful for us when we talk about changing our cotangent function. So having those asymptotes and knowing that they're usually at 0 and pi is good, and knowing that on the tangent function they're at negative pi over 2 and pi over 2, definitely something you want to know. So negative pi over 2 and pi over 2, that's going to help us figure out any horizontal shifts for us. Okay, those base asymptotes. All right, so let's actually sketch a couple. So sketch the graph of the function, state the domain range, and asymptotes. Sketch the graph of the function, state the domain range, and asymptotes. I don't know if in your homework they're going to ask for more than one period. They typically do ask for 2 periods. I don't need that. One well-labeled period is all that I need because you have graphing calculators, okay? Label it well, and that'll be just fine. You can see both of these have a number in front. Again, that is still we don't call it amplitude, but it is a vertical stretch. And so for this cotangent function, it's not going to go through 1 anymore. It'll be stretched by a factor of 3, and so it's now going through that 3 on the y-axis. So it's a vertical stretch. And you can see we've got some changes with x. And so those changes with x are going to change where our asymptotes are. And to find those, the starting and ending asymptotes, we're going to go back to our original cotangent function. Where are the asymptotes for the cotangent function? 0 and pi. Normally it starts at 0 and it ends at pi, but it's got these changes in between. Changes with x. And so these 0 and pi are specific to the cotangent function, and that's going to change based on what you're looking at. How do we solve for x? Divide by pi. And so 0 divided by anything is 0, x, and pi divided by pi is 1. That's very interesting. So we are now getting asymptotes at 0 on the x-axis and 1. So there's a vertical asymptote at 0 and a vertical asymptote at 1. Where's the other vertical asymptote if I were to continue on? 2, yes, there'd be another vertical asymptote at 2, but we don't really, I don't need it, but just so you know what would happen here. It was normally multiples of pi, so 1 pi, 2 pi, 3 pi, and you can imagine if we divided all those by pi. All right, then I know that I have a vertical stretch of 3. So vertically, we've got some nice points at 3 and negative 3. So what I'm going to do is subdivide, just like we've done in the past. What's halfway between 0 and 1? 1/2. What's halfway between 0 and 1/2? 1/4. 1/4, 2/4, 3/4. So right in the middle is our center point. And cotangent is a decreasing function. It should be going downhill. So at 1/4, it's our high value. and then our middle, and then 3/4 is our low value. Just like that. At 1.5 would be another midpoint, and again, that's good. It really, I don't need much. The asymptotes are the important part. And the reason I did a little bit more is so we could actually check this. Again, if I wanted to check cotangent in my calculator, I have to be a little bit fancy. I'm going to do 1 over the tangent of x. Oh, interesting. It has a 3 in front. Thinking about that, that would be 3 times 1 over the tangent of pi x. 3 times 1 over the tangent of pi x. I'm just going to put that 3 on top because if I multiply 1 times 3 gives me 3. So 3 over the tangent of pi x is how I would type that into my calculator. And I'm just going to stick to my Zoom trig. Oh, no. I'm going to change my window. And just go from 0 to 2, counting by ones, and -4 to 4 is fine. Okay. So changing my window so it looks pretty similar. So there's 1 and there's 2. So you can see it's pretty good. I can check this point, 1/4 3. So 1/4. And I get an output of 3. Yay, I did it right. Okay, good. All right, so again, this 2 is a vertical stretch by a factor of 2. What does the negative do? It flips it. Yeah, it's a reflection across the x-axis. And so our tangent function normally goes uphill from left to right. But what's this one going to do? Yeah, it's going to be flipped upside down. So it's not going to be that one. It's going to be the negative one, which is going to go downhill from left to right. Again, we have all these changes with x. So we need to know where was tangents starting and ending asymptotes? Which were the good ones to remember for tangent? So we go back to tangent, negative pi over 2 and pi over 2. Negative pi over 2. It's got all this stuff in here. Whoops. With x and pi over 2. So you do have a bit that you need to remember. We're going to go ahead and isolate x and add pi over 2. Negative pi over 2 and positive pi over 2 is 0. And pi over 2 plus pi over 2 is 2 pi over 2, which is pi. All right. Oh, that's interesting. So I have an asymptote at 0 and an asymptote at pi. We need to go back and state the domain, I guess. Forgot. And I want to subdivide just a little bit. What's halfway between 0 and pi? Pi over 2. Half of that is pi over 4. And right here, we've done this before, halfway between pi over 2 and 2 pi over 2 is 3 pi over 4, if you do the math. We have a vertical stretch of 2, and our tangent function has a reflection, so it's going to be going downhill. So it's going to start up high, and then middle, and then low. So there's one period of this particular tangent function. Let's see. The vertical asymptotes are occurring at x equals pi, 1 pi, and 2 pi, and 3 pi. I'm going to say k pi, where k is an integer. And I think I'm just going to say the domain is not that. All real